happens in the very large, in the solar system and beyond, in our galaxy and beyond, in clusters of galaxies and beyond in cosmology. No, that is a frontier also, very exciting. But what I'm going to tell you about is not pertaining to that directly, nor does it pertain to the very many. The kind of amazing emergent behavior you can get when you put many simple constituents together, whether they are atoms or molecules, as happens in condensed matter physics or chemistry, or if you put neurons together, as happens in neurobiology, or if you put artificial neurons together, which, as you know, is an exciting frontier of artificial intelligence. I'm not directly going to tell you about any of them. Instead, I want to discuss a new frontier, which let's call, and I hope some of this will be clear in the course of my talk, let's call it the entanglement frontier. This frontier pertains instead to our growing understanding of quantum mechanics, its true meaning and significance. Now, Atri, you have to change your slide. I'm sorry. I should have told you before. Hi, Atri, can you hear me?
Yes, this is the slide you want?
It's still showing entanglement frontier in my screen.
Oh, anyone else?
Entanglement.
Okay,
Ma'am,
now
it has come to slide. Yeah, it's fine.
I think
the point is that there is some, so there is some issues. So I have to share from this platform only. You will see some additional nonsense here. So okay. I can't help. So we go here.
Yes, here. Yes. Yeah. Slide number 3. Yeah, in the presentation. So, so instead, this frontier pertains to our growing understanding of quantum mechanics, its true meaning and significance. And since quantum mechanics provides the bedrock of our understanding of all of the natural sciences, this frontier, in fact, promises to have important implications for many diverse branches of science, whether they fall within physics, chemistry, computer science, as you'll see in my talk, some aspects of engineering, and actually even mathematics. And so it's really a broad, new, exciting frontier. And here is the next slide is my attempt to show that to you. Various disciplines, chemistry, computer science, foundations of quantum mechanics, of course, condensed matter physics, chemistry, again, I repeated that, quantum gravity, in fact, my own area of work. And at the end, center of that all seats these new, this new set of developments. Okay, next slide, please, Atri. So now, one of the main things I want to try and convey is that there's going to be a huge amount of progress, I think, in the coming few decades in this new frontier, in advancing it. And it's a wonderful opportunity for India to make big contributions, especially for young scientists and engineers. And so I especially am excited that you're having this meeting where we are interacting with teachers and so on, who, after all, have to carry the main share of this responsibility to convey the excitement and enthusiasm and train our students for the future in this exciting area. Now, with that introduction, I'll go further by way of an introduction and tell you what is the essential features, which are kind of weirdnesses of quantum mechanics when we compare them to a classical understanding or intuition, that underlie some of this hope that quantum technologies will prove so remarkable. And these are summarized in many ways in the famous work of John Bell and his theorems, which I will briefly allude to. At least I won't prove it here. Someone else may perhaps do it in this course, or it's easy enough to do. And I hope you all will go through the proof. I'll come to that in more detail. And so it pertains, some of the weirdness is essentially encapsulated in Bell's work and in the idea of entanglement. And because it's this feature of quantum mechanics, which is really what distinguishes classical physics from quantum mechanics, it's the aspects tied to entanglement. That's why this frontier, I think, can be quite aptly called the entanglement frontier. So that's the first part of the talk. The second part of the talk, we'll explore the idea of entanglement, by discussing how it might help us build really new kinds of computers, quantum computers. Some of you have already heard about this, of course, I'm sure, but we'll just discuss that as a kind of brief overview. Why these computers hold promise, how they might be able to solve what are, for classical computers, very difficult problems with a kind of exponential speed up, the implications of that for our world, and so on. So that's the first part A in the second part of the talk. Then I was going to talk about quantifying entanglement entropy, but maybe in the interest of time, we'll kind of skip over that a bit. And so the second major topic here that perhaps we can talk a little bit about is how our growing understanding of quantum mechanics, in a sense, these novel, weird, if you like, features, is beginning to change our understanding of condensed matter physics. And also, just briefly at least, tell you how it pertains to even our understanding of quantum gravity and how it is beginning to influence that. And then finally, we'll end with some conclusions and a postscript, which I already let out in terms of the National Quantum Mission in my introductory comments, but we'll come to it. Okay, next slide, please. Thank you. It might seem strange to many of you that there is this renewed excitement in understanding quantum mechanics and its implications. After all, quantum mechanics is about 100 years old. Surely we've understood it well enough. How can there be any real excitement now pertaining to the very basics of quantum mechanics? And the reason is, yes, it's been around for 100 years, but quantum mechanics is so strange, so removed from our day-to-day understanding from which we draw our basic intuition, that it's taken about 100 years to even truly begin to appreciate this strangeness, and to bring us to a point where we now hope to use this strangeness to do fundamentally different, novel things using quantum physics in technology. And it's this big difference that I want to try and bring out a little bit in the talk today. We are only slowly beginning to come to grips with quantum mechanics. And so there's a lot of room to do a lot of things as we, in a sense, internalize this essential weirdness and strangeness of quantum mechanics. But just to go back, the feeling that quantum mechanics is really very strange, of course, was something that from the beginning, all the great minds who developed quantum mechanics clearly understood. So let's go back. Here's a famous quote by Niels Bohr. Niels Bohr, as you know, was one of the father figures of quantum mechanics. And this is a quote not from when quantum mechanics was being developed in its early days, but in 1952. Okay, so already a few decades after, Niels Bohr really struggled trying to understand it, understood it very deeply. And he said, for those who are not shocked when they first come across quantum theory, cannot possibly have understood it. Okay, here he's saying why he feels it's so strange, not shocked. It's really a very profoundly different kind of, framework. It reduces in some limits to our classical world, but in its true quantum, domain, it's a very different framework for understanding nature, for understanding all physics and various phenomena of nature. Well, here's Richard Feynman, who really also advanced quantum mechanics in very significant ways. And, Feynman is famous for saying it like it is. And so he says, I think I can safely say that nobody understands quantum mechanics. Of course, with Feynman, it's also partly, I think I can safely say, I don't understand it, therefore nobody understands quantum mechanics. Anyway, and by the way, this quote is drawn from this book, from this set of lectures, although given in 1965, which I recommend to all of you. It's called The Character of Physical Law. These were a set of lectures he gave in Cornell, and they beautifully encapsulate the nature of physics, the essential features of physics and the natural laws we discuss and describe in physics. So for all your students, please make them read this lecture. I think it's 1 or 2 lectures. I read it when I was going into college, and it had a, I would say, transformative effect in me. So if nothing else, this is one recommendation I would like to make to you. Okay. Now, why is quantum mechanics so difficult to understand, to reconcile with our intuition? Well, one reason which we all learn about when we do our first course in quantum mechanics is, oh, it's the next slide, thank you, is that the quantum world is intrinsically probabilistic. And I'll say more about this. It's in fact even a little more subtle. The fundamental description of reality is in terms of a wave function, which we should think of as a probability amplitude. And then you have to take that wave function and take its absolute value and square it to get a probability. So, probability amplitudes are the way in which quantum mechanics is framed. And there is no analog of this in our day-to-day life. Okay, so here, next slide, please. So next slide, please. Yeah, thank you. So the probability, say, to find a particle at some location x is obtained by taking the wave function, which depends on x, for any state, and then taking its absolute value square. Okay, and it's a little bit like we are used to amplitudes and squaring them in classical physics in the context of wave phenomena, right? So for example, you have water waves. Next slide, please. You have water waves, I'm showing here, and the water waves can reach any point in many different ways, traveling in different ways. You have some amplitude, it reaches a point from some earlier, say, reaches a point P from one point P0, some amplitude, it reaches it from P1, and so on. You have to combine all those amplitudes to obtain the net amplitude at the point of interest, and then square it to obtain the intensity of that water wave, right? The amount of power carried in that water wave. So we understand that for water waves, for sound waves, for light waves, and in general in wave phenomena in classical physics. But here we have to apply that idea in quantum mechanics to the notion of probabilities themselves. Nothing is certain. The probability that a phenomena will occur is obtained by adding amplitudes as if they were waves from earlier points. You can receive some amplitude for a particle to be at point x, from it being at x1 at some earlier time, t1, x2 at time t1, etc., etc. You have to add up all those amplitudes as if they were like water waves, then take that absolute value square, as I said, to obtain the probability. So this is very strange when we are dealing with reality, physical reality, where we are used to thinking more in terms of certainties. Okay, next slide, please. Yeah, you've gone there already. And it's a little bit like in Young's double slit experiment we do in light. We have light coming from, say, 2 slits here, which we have to add up to get an interference pattern. In quantum mechanics, you can have an amplitude for, say, an electron to pass through S1 or S2, and then the total probability on the screen is obtained by summing up the two amplitudes and taking their the absolute value square. And this, as you know, is this famous double slit experiment, which is depicted here in the next slide, please. So we have electrons being fired from the gun. Here is the wall with 2 holes, and the electrons are collected on this black stop, and the pattern you get is this last pattern, which is very much like an interference pattern. If you close either of those two, you get a probability P1 or P2. P1 if you close the second slit, P2 if you close the first slit. When you keep the two open, what you get is not the sum of the two probabilities, okay? the sum of the two probabilities, if you look at
ये
that,
बोली तो था
if you look at the second last drawing, there's someone.
Who is here? Please stop your audio. Hello, somebody is speaking.
I request Ms. Shushmita Pal to please mute herself.
Okay, excellent. Thank you. So, you see, okay, some quantum interference. Okay, so
देखा जाता है जो लोग मार देंगे
Please,
I request Ms. Shushmita Pal to please mute herself.
नेवर बोला है
Admin, please. Admin, please.
I think organizers can mute someone if they want.
Yeah, that is what. Admin, please
Yeah.
put her off.
Admin, please mute her.
Shushmita Pal, madam, what is your problem? Please put yourself off. Madam Shushmita Pal.
I think
Okay,
from
I have
admin side can stop.
I
it.
think he is not listening. He is not
Admin
listening.
side. He's not listening, I think.
It's all right, done.
okay, excellent. Okay, so you see, if you look at that second last figure, you will have P1 and P2, and if you add P1 and P2, you don't get the last figure, and that's why it's an interference. You have to take the amplitudes, sum them, and then you get mod psi square. And this is like what you do in water waves, right? Somewhere you can get constructive interference, and somewhere you can get destructive interference, and the resulting pattern is then obtained by taking all that into account. So this is true in quantum mechanics, and it's very different from classical physics. Now, this is a fact, of course, which is strange, and it's difficult to internalize, but it's something we have been used to for a while. And now I want to say one thing, that even though I'm going to go on and discuss with you the second strange aspect, which is entanglement, many of the advances currently going on in quantum technologies just use this interference aspect to use. And this surprises me. They don't use entanglement, the second feature I'll come to, just using superposition. This surprises me because this feature has been understood for quite a long time, but it hasn't been put to use in technology. And I'll give you an example. Working in a DRDO lab, just using superposition, we built a random number generator, which is cheap, easy to build, and as good as the best in the world, just putting to use this superposition principle of quantum mechanics. So I give that example just to say there's a lot to do by way of technology, which people somehow haven't thought hard enough about. Okay, so now just to go on with my presentation, in classical mechanics, we assign a definite position and momentum to every particle, right? Let's say you have a trajectory in red. At any point, you have a position x, you have a momentum p. But in quantum mechanics, this interference phenomena I talked to you about is tied to the fact that we cannot assign a definite position and momentum simultaneously to a particle due to the uncertainty principle. Okay, as you all know, I think the famous Heisenberg uncertainty principle that delta x, delta p is greater than equal to h bar over 2. This means there's not a definite trajectory for every particle. There is an uncertainty in that trajectory, and that is tied to this wave-like behavior that probability amplitudes end up exhibiting. So therefore, in quantum mechanics, we deal with probabilities and rather probability amplitudes. Now, of course, just to say, probabilities arise in our day-to-day world all the time, right? If I flip a coin, there's some probability it will land head up or tail up. The trajectory of a coin, which is a heavy object going through the air, is described basically classically, right? It is a classical object, but we assign a probability to whether it's going to land heads up or tails up, and that's because this process of the coin moving through the air is a very complicated process. If we wanted to get a definite outcome, we would have to keep track of all the air molecules the coin interacts with in the course of its motion. We would have to keep track of exactly how we hit it, the initial conditions, and so on. All that is virtually impossible to keep track of. So therefore, given our ignorance, we end up associating a probability. But what is different in quantum mechanics is that the probabilities are inherent. They are intrinsic, not due to our having to keep track, not due to our ignorance of some part of the system. They are just intrinsic to the formulation of quantum mechanics. It's not as if you tried to do better and kept track of more degrees of freedom, you could get around this kind of probabilistic interpretation. Okay, now let's come to the second property, which is the one which is, only slowly coming to the fore, the property which people are now really waking up to, in a sense. And this has to do, as I said, with entanglement. And it arises from the fact that the wave function, which describes the system, and I'll explain this, is inherently non-local in quantum mechanics, even though all consequences that follow from this wave function are local. This means quantum systems have correlations which are non-local without any classical counterparts or analogs. And these correlations are what are called entanglement. So this slide, in a sense, is a kind of key slide. It has many words: entanglement, non-local correlations, etc. And I'm going to spend some time now discussing this, because this in many ways is the heart of the whole matter. Now we're only slowly beginning to, next slide please. We are only, next slide please, Atri, thank you. We are only slowly beginning to understand this property, and much of the recent progress is coming as our understanding of entanglement grows. So much of our talk today will be about this. Okay, let's go ahead. Now, it was really Einstein, Podolsky, and Rosen, but really Einstein's remarkable physical insights, which led him to first put his finger on this weirdness. And it caused him a lot of disquiet. As you know, already the probabilistic aspect caused Einstein a lot of disquiet. He said things like God doesn't play with dice and so on. But entanglement was really something even stranger, and he felt a signal that perhaps there was something wrong in quantum mechanics. A kind of spooky action at a distance. Now, I'll try to explain what I mean. Einstein understood better than almost anybody else that you could not have signals that travel faster than the speed of light in physics. And the reason is, if you believe in the special theory of relativity, then the speed of light is the absolute maximum limit with which any signal can travel. So he understood that you could not have any physical effect that propagated faster than the speed of light. And when I say local, I mean things which happen, say I have 2 points, A and B, say I'm sitting wherever I am right now, and you are in Silchar, then any signal, my voice, cannot reach you faster than the speed of light, okay? Nothing I do can allow that to happen. Yet, the description in quantum mechanics, in general, is one which must, a total description must have a kind of non-locality to it, which I will explain next. And this caused grave discomfort to Einstein. He felt if all phenomena are ultimately local, then the description of ultimate reality must be local as well. Whereas quantum mechanics only seems to work with this kind of non-local description. So this is what I want to turn to next. I try to explain to you what I mean by the non-locality inherent in the wave function in quantum mechanics. So next slide, please. Next slide, please. I think you went ahead of me. So go back, please. Yes. That one. This is, yes, perfect. So before I go to quantum mechanics and why the description is non-local, let me, to explain the words local and non-local, first discuss classical mechanics, where the description is local. So let me explain what this means. So far we talked about one particle and its trajectory in classical mechanics, but now let me take two particles. Okay, particle 1 and particle 2 shown in this slide. Now, particle 1, I said we would describe by its position and momentum, x1 and p1. Particle 2 would be described by its position, x2 and p2. The full description of the system is obtained by simply taking what x1 and p1 are for the first particle, giving that information, and giving the information of what x2 and p2 are for the second particle. This is what I mean by describing the system locally. You simply describe the local variables, put that description together to obtain the description for the two particle system, right? Signals can, of course, go from 1 to 2. Like the first, for example, particle, if it's charged, it can move around. That would send an electromagnetic signal. The electromagnetic signal would go from 1 to 2. Maybe 2 can absorb it, and so on. All that I'm calling local, because all those effects will not propagate faster than the speed of light. So that's a local physical effect. And the fact that you can describe the system by just putting together the individual descriptions, that's what I mean by a local description for the system. Okay, so those are the words. I hope I've been able to put them across. Now let's turn to quantum mechanics. Next slide, please. Now, in contrast, in quantum mechanics, suppose we have two electrons and the electrons are very far apart from each other. Okay, so in the next slide, I'll show you one electron, just to be dramatic, is here on Earth, and the other electron is in Andromeda galaxy. So very far away, just to be a little dramatic, clearly separated systems. But it can be the case, even though they're separated, that the two are in what's called a spin zero state. Okay, which means which means the following operationally, that if we measure the spin of the first electron on Earth, say along the z-axis, and find its plus half, we immediately know that the spin of the second is minus half. Okay, immediately know. And on the other hand, if we measure it on Earth and get minus half, we immediately know that it's plus half in Andromeda, even though Andromeda is so far away from us. Okay, and this is the kind of spooky non-locality that worried Einstein. Okay, he said it should just be no signal can travel faster than light. I should be able to describe the electron on Earth by degrees of freedom on Earth, and the electron in Andromeda by degrees of freedom in Andromeda, like I did in classical mechanics for particle 1 and 2, and then just describe all of physics as some signals propagating from Earth to Andromeda. So next slide, please. So here I'm trying to just illustrate this for you. If you know a little bit of quantum mechanics, you'll know that this is the spin zero state. Electron on Earth is plus, electron on Andromeda is minus. That's one part of the wave function amplitude. Minus for spin zero, electron on Earth is minus, electron on Andromeda is plus. And so you see they are correlated. They are correlated with each other, and since one is on Earth and the other is in Andromeda, it's a non-local correlation. As I was mentioning to you in quantum mechanics, we get non-local correlation. So here you see this non-local correlation. You cannot describe this system as some description involving just the electron on Earth times, say, some description just involving the electron in Andromeda. No, it has to involve this joint aspect. Okay, and this kind of a state with a non-local correlation is what we mean when we say it's an entangled state. Okay, and it doesn't have an analog in classical physics because there's a manifest kind of local description. Okay, next slide, please. Next slide, please. Thank you. Now you might ask, well, if it's really the case that I can measure the electron here on Earth and find its plus half, and then instantly I know that the electron in Andromeda is minus half, well, why is it that I've not sent an instantaneous signal from Earth to Andromeda? And that's a very good question. And the answer to that is tied to the first strange property of quantum mechanics, that the knowledge of a system is probabilistic anyway. And I wish I had a little more time to work through the mathematics and show that to you. But because the knowledge in that state, I showed you plus, minus, 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 plus is not certain. Either electron on Earth or in Andromeda can be either plus half or minus half. When you actually work through the consequences, you find, okay, if you carry out the measurement on Earth, you'll get probability half to be plus, probability half to be minus. And that fact, therefore, means that on Andromeda also you have this kind of equal probability. So it ends up, but it requires some thought, and I won't go through it, that the first strange property of quantum mechanics saves you, despite the non-local correlations, from being able to send a signal faster than the speed of light. Okay, so there's a very beautiful consistency in quantum mechanics, which has non-local correlations, but does not allow signals to be sent faster than the speed of light, or does not allow, weird things like causality to be overturned. Okay, the two, all our usual notions of cause and effect, something coming later than before, signals traveling, slower than or equal to the speed of light, all this is respected in quantum mechanics, and yet we have these kind of non-local correlations. Nevertheless, Einstein was deeply troubled, as I said, but his objections were philosophical. He knew there wasn't an experiment he could suggest which would show quantum mechanics was inconsistent. But his point was, if ultimately all consequences are, as I'm saying, local, or why do you need this strange non-local description? Okay, next, please. Next, please. Okay. If I'd asked, we got a bit out of sync, but in the slide previous to this, Einstein then went on to suggest that that maybe quantum mechanics was not the full description of nature. Maybe there was an underlying description with extra degrees of freedom we hadn't kept track of. And if we kept track of that, we could obtain a good local description like in classical physics. So this led to the entire study of local hidden variable theories, etc., that happened in the past few decades. Okay, in the past few decades, still the work of John Bell, which I'm coming to next. Okay, next slide, please. Yeah, we can skip over this. That's fine. Thank you. Okay, we can skip over this also. So people started thinking maybe quantum mechanics is not complete and so on. And it was in that direction that more thought went until the really beautiful and very, very remarkable work of John Bell in 1964, which I will now discuss for you, which really lays then the understanding of, lays down the understanding of this second very strange aspect of quantum mechanics, entanglement. And what he showed was that it is entanglement that could be used to distinguish in a genuine way quantum theory from any classical theory, even with local hidden variables. That is to say, even if you say, well, maybe our description is incomplete and we can have some version of a local theory with local degrees of freedom, working as per the rules of classical mechanics that may describe nature, there would be experimental differences between any such description and quantum mechanics. So his result is so powerful because it isn't just ruling out some possible extension of classical physics, it rules out all of them in one fell swoop, in a beautiful theorem which requires basically not even high school level of mathematics. This is the other thing to say. Every school student can understand Bell's theorem. It requires trigonometry at the level of cos square theta plus sine square theta is 1. Okay, that's the level of algebra involved. And yet it's one of the most remarkable results in physics of the 20th century. Okay, one of by far the most remarkable results. And this single result of his underlies the entire entanglement frontier, which we look at today with so much excitement. So, just to say, this is the other thing I want to emphasize, is that, physics doesn't always need very sophisticated mathematics. And, quantum mechanics is invented at the turn of the century or so. It takes till 64, about 50 years or so, for John Bell's work, landmark result. Not because some fancy mathematics has to be invented, but just because quantum mechanics is so strange that despite decades and decades, Niels Bohr, Einstein pondering it, it takes up till 64 for John Bell to put his finger on things and say, look, there is an essential feature of quantum mechanics. You can test it experimentally. It cannot be reproduced by any classical system. So now, instead of being philosophical kind of objections, this turns the entire discussion into an experimental discussion. So it's a very landmark result. And next, I want to turn to just telling you at least what this result is all about. And Bell's theorem is formulated in terms of some inequalities. You carry out measurements on a physical system, and no matter what the classical description is, it may be the description we use today, it may be that there are extra hidden variables, local variables, local meaning again in the sense of classical physics, for every electron or every particle we'll assign local degrees of freedom. Maybe instead of position and momentum, we assign a local color or something. But if no matter what that classical description is, okay, the inequalities cannot be violated by that classical system. Whereas in quantum mechanics, using known rules of quantum mechanics, Bell argued, and this is where high school level algebra comes in. Bell argued using high school level algebra that they can be violated and are violated, and quantified the extent of violation. Okay, so let me explain that, and then I'll briefly show you the experiment for which the Nobel Prize was given recently, which showed that, in fact, quantum mechanics is correct, setting the stage now for all these developments. Okay, next slide, please. So here is the thought experiment for which you can apply Bell's reasoning. So we have, again, two electrons like the ones on Earth and Andromeda, but now in this case, we'll have them on Earth, but separated. So we can think of them as distinct local degrees of local systems, not local systems. And the first electron is spinning with a spin plus, say, in the A direction. Earlier I had it in the Z direction, but Z was just some choice. It could be any direction. And the second electron is spinning with a spin plus, if it's C plus here, in the C direction, some other direction. And P, A plus, C plus is the probability. If you carry out a measurement on the two, that you'll find the electron A. You'll find the first electron, on the left, spinning with spin plus in the A direction. So you have some magnetometer and so on, and you orient it and you carry out a measurement. You orient it along the A direction, and you ask, what's the probability that I'll get the electron, the left electron to be up? You then do a measurement on the second electron, similarly, and then you get some probability for it to be up. And in general, in this way, you can compute the probabilities and calculate them, and also experimentally, find what they are for the first to be up along A and the second to be up along C. Okay, and then so this is the basic quantity, this probability, and then you can do it for various directions. And we are going to take these two electrons to be together in that spin zero state I was mentioning, up, down, minus, down, up. Now, it doesn't quite have to be that state. It can be any entangled state and so on. But for now, let's keep it simple. We take that state. Okay, next slide, please. And then what Bell showed was that any classical system, okay, has this kind of inequality, that the probability along for the electron, first electron to be plus along A and plus along B has to be less than equal to, two other probabilities. This kind of inequality then involves three directions, A, B, and C, and spins measured along these three directions, okay? A and B plus plus, A and C plus plus, C and B plus plus. And A and B plus plus is less than the other two. Now, the reason he could show this so generally in classical physics is that probabilities, even if they arise because you have extra variables that you're not keeping track of, like if you spun a coin going through the air, there might be variables having to do with how the air interacts, which you don't keep track of. Similarly, if you're thinking of various versions of classical physics, maybe you have extra variables. But even if you have them, probabilities that will emerge because of not having kept track of degrees of freedom in the classical world will always have to be positive. Probabilities can never become negative. And for that reason, you get an inequality like this very generally in the classical world. Now, in contrast, sorry, let's go to the next slide, please. In contrast, he showed, first of all, that in quantum mechanics, if you chose the three directions, A, B, and C carefully, you could violate them, and you would violate them in the two-state system. And therefore, as I said, it became an experimental question. And here is the beautiful experiment done by Alain Aspect, Grangier, and Rogers. And it tests not quite the inequality I told you, but is a closely related one, the BCH-SH version. But anyway, that's the basic idea. Here on the x-axis is an angle, which roughly you can think of as angles corresponding to the choice of A, B, and C. The experiment is not quite the same, so it's not like you have three directions. But anyway, roughly think of it as a choice of direction. And think of S as the analog of those probabilities I was writing down. Now, in any classical theory, this S as a function of the angle, theta, has to lie between 2 and -2. It's not quite a probability. It's something related, so it can take values greater than 1, but it has to lie between -2 and 2, okay, in any classical theory. Whereas in quantum mechanics, the curve which is drawn here is the theoretical curve. Okay, these experiments were not done with electrons, they're done with photons, which are taken to be polarized, which is the analog of their spin in a particular state, which is the analog of the spin zero state. But those are just details. So, you have in quantum mechanics a amplitude which you can precisely calculate for the experiment, and from that a probability. And the curve which is shown here is the theoretical curve. The data points, I hope you can see them in dots, are the experimental points. And you see how beautifully the points lie, the data points lie exactly on the quantum mechanics curve. Okay, ruling out and in particular, they go through, for suitable choices of angle, this region, okay, where quantum mechanics differs from classical physics, the classically forbidden regions. And it's this experiment actually which really conclusively proved that no version of hidden variable theories, no extension of classical theories could be possibly correct in describing nature, and quantum mechanics was really different, truly fundamentally intrinsically different from any such classical setup. And next slide, please. And in recognition of this landmark experiment, the 2022 Nobel Prize was given in physics to Aspect, Clozier, and Zeilinger. I've not talked about the work of the other two, but in BCSHH, that inequality, the C is Clozier, and Alain Aspect, of course, for the experiment. So anyway, this is landmark. And if you go to the next slide, please. Okay, I wanted to tell this story. I might, anyway, let me just tell it. I don't have to go through my whole talk, but it's nice to liven it up with some human interest. And I want to tell you the story about how Alain Aspect started working on this. And another thing I really want to request you all to do and to make your students do is to please make them hear Aspect's Nobel Prize talk. It's on YouTube, and the Nobel laureates give a talk traditionally when they receive the Nobel Prize, and he does so. And it's a beautiful talk, and his personality comes through, and he also explains the version of Bell's inequality they tested very beautifully. You'll see the simplicity of the mathematics, but also he explains the experiment and all the challenges. And physics in the end is an experimental field. And so, the ingenuity that goes into it, all of that. So please do, after they read or even before the character of physical law, they must hear the YouTube video. Okay, now I want to tell you this story because it also brings out something. Aspect was a very young person when he started. Well, he was like, I forget exactly, but 25, 26, when he said he heard about Bell's work. And he said, he's written about this, he said, my world came to a stop. I said, I must do the experiment. What can be more important than testing whether quantum mechanics is correct and different from classical physics of any kind one can conceive? I must do it. Now, it was a very, this was a fringe area. Today, it's so center stage. At that time, only people who were sort of dabbling in the philosophy of physics were thinking about these kinds of issues. So it was not recommended usually for a young man to do it. But he was burning. He was in Paris. He took the train up to Geneva and he met Bell, who was working at CERN. And he told Bell breathlessly, right as they met him, he said, I gave no time to Bell for niceties of introduction. I breathlessly for half an hour told him what kind of experiment I was thinking of with photons, how I would do it, this, that, and the other. And then after 45 minutes, there was a pause. And eventually I stopped talking. And the first question which came, this is what Aspect recounts, from Bell was, do you have a permanent position? And, this is because otherwise it was so unfashionable. That it would not have been a good idea to work on this. So I just thought I'd mention this because, sometimes, not always, but sometimes by going off on tangents, not doing what is just regarded as the most fashionable idea of the day, one can do really, really great work, which of course he then pulled off. Okay, next slide, please. So just to say that, of course, this experiment was repeated after that, and beautifully vindicates quantum mechanics. And in some cases, the difference between, you saw the quantum mechanics results going through the forbidden region, and in some cases, distinguishes classical physics from quantum up to 9 standard deviations. So there's really no doubt that quantum mechanics is correct, and any extension of classical physics with local hidden variable theories is out. And therefore, given all this, now people have begun to ask, okay, if quantum mechanics is so different because of entanglement from any possible classical system, can we put it to use in doing things that no classical system could accomplish. And this is why now the attention is increasingly turning to quantum technologies of various types. Okay, which is what we'll turn to, and then I'll stop. So anyway, I've already explained that this kind of non-local thing is called entanglement. We can go ahead, please. Maybe next slide also, please. Okay, now this one, just to introduce some terminology which you probably all know, is that, the kind of system I was referring to, an electron which can be spinning up or down. This kind of a system where, you can have two states is what is called a qubit, a word you might have heard. It doesn't have to be an electron. It can be any physical system which can have two quantum states. And if the two quantum states have these kind of correlations, non-local correlations, as I was describing them, shown here for the spin zero state, then they are entangled. And this particular state in honor of Bell is called the Bell pair. These are just some words you'll hear, and I'm sure many of you already know about. Okay. So now let's go forward to the, yes, maybe we can go to the next slide, please. Now it's increasing, just to reiterate what I already said, being realized that in fact, these kind of non-local correlations or entanglement is a kind of resource which can be used to do things which are impossible to achieve in the classical world. For example, build computers using quantum mechanics which can run much more rapidly, more correctly do computations in finite time, which are very much harder to do compared to their classical counterparts. And so let me give you an example of quantum computers and why they could achieve this kind of speed up because of entanglement. And then I think I'll just stop. So let's go to the next slide, please. Oh, this one I want to show you. Maybe we can skip this one. Yeah, this one I want to show you because I'm using the word entanglement frontier, but it was coined actually by my advisor, PhD advisor, John Preskill, who happens to be the Feynman professor. So I thought I should give him due credit for the phrase. Okay, now let's go on. So let's talk a bit about quantum computers. I'm sure some of you already know about this, but the idea, as I said, is to try and use entanglement in particular, but more generally, the weirdness of quantum mechanics, superposition as well, to try and do things which we can't do with classical computers. So that's the basic idea here. And okay, we can skip the next slide, but please change. Yeah, we can skip this. Yeah. So now, why is it that we might have this hope that we can, do a faster, say, computation? There are a couple of ways to say this, one of which goes back to Feynman. Feynman actually was one of the first people who thought about whether quantum computers could be built and how, whether they could be faster. And Feynman actually, interestingly, I mean, he knew about Bell's work, but, I want to tell this also to you all, because how sometimes very important thoughts can arise, in simple ways and by talking to a broader set of people. So how Feynman came to start thinking about whether quantum computers could be built is as follows. He was interacting with a lot of different kinds of scientists, not just physicists. He was interacting with chemists, he was interacting with biologists, and there were some chemists who were trying to simulate on classical computers. This is around the 1970s or maybe early 80s. They were trying to simulate molecules, and find their ground states and so on. And they found that they were running out of computational resources and of that time. But even by today's standard, with today's resources, by the way, when you go to a system with even a few atoms or constituents, it gets challenging pretty quickly. Certainly it got challenging then. And so they were expressing their frustration to Feynman, and he would talk to them once in a while. And finally, it occurred to him that surely we were missing something in our way of building computers, because nature finds the ground state of these molecules so efficiently, right? Within atomic time scales, okay, if you take a system and you excite it, a molecular system, it'll settle down into its ground state. And you can think of that as a computation, right? Because after all, what is a computation? A computation is you have some system, you have some initial condition, and it goes to a final state, which is the answer to your computation, right? So how is it that physical systems working on the principles of quantum mechanics, which molecules work with, are able to find their ground state so efficiently, whereas we humans working with classical computers just could not do it? And it made him think that the quantum world was working in ways that the classical world just wasn't, and that was the key. So this is how Feynman came to the idea that it's really worth thinking about quantum computing. And I always feel it's such a beautiful example of how you can be inspired to think about something, say in quantum mechanics or physics, because of input which comes from different fields. Okay, and one of the key ideas, actually, he didn't quite use this phrase, but it's clear in his thinking in the 80s that it was there. One of his key ideas was that the space of states in quantum mechanics is very big. If you have a single qubit, the total number of states, as I said, is 2. If you take 2 qubits together, then the number of states is 4. But if you take 3 together, then it's not 2 plus 2 plus 2, 6. It becomes 8. 2 into 2 into 2. Okay, 3 qubits together are in 8 possible states. And if you take 4, they are in 2 to the 4 states. And so the number of states a quantum system with n degrees of freedom can exhibit, or the number of states it can be in, grows exponentially. If you have n qubits, the number of states would be 2 to the n, okay? Not n times 2, but 2 to the power n. So the fact that it can grow exponentially, this is what he meant when he said that it's a big place. And that means if you're trying to find properties having to do with, say, ground states or some particular set of states of a quantum system with, even a few different constituents, you're going to have to deal with a very big set of total possibilities. And that is what makes it so challenging if you're using a quantum computer. So here in next slide, please, I explain the fact that the total dimension is exponential, 2 to the n. And 2 to the n, as you know, can very rapidly become a very big number. Now, how then in the quantum world, if you have so many possibilities, how does the quantum world manage to so efficiently, say, find ground states or process information in such a big space? And here we come to Feynman's second beautiful idea, or rather, really one of his main beautiful contributions, which is, as you all know, he reformulated quantum mechanics. There was the formulation of Schrödinger based on the wave function, and of Heisenberg based on matrix mechanics, as I'm sure you know. But Feynman did in what is one of the, again, most remarkable original pieces of work. Again, more or less as a graduate student, he reformulated quantum mechanics as a sum over parts. He really took this idea that you have these wave-like amplitudes which can be summed, and made that into a reasonably precise way of doing quantum mechanics. And so, for example, here in this slide, if you have a particle which has to get to B from point A, then in the classical world, let's say this is a cricket ball, you'll throw it with some velocity at A, and accordingly it'll take some one trajectory and get to B. But if it's an electron or some quantum particle, it doesn't just go along one trajectory, as Feynman showed. It has an amplitude to reach B from A in many different ways. You have to sum up all these amplitudes, like those like the electron going through the 2 slits, and then obtain the total probability. Amplitude, and from that the probability. This means there's a kind of massive parallelism in the quantum world. the evolution of the particle from A to B is not just sensing one path like it would do in the classical world, but it's sensing simultaneously many different paths. And this fact is what allows, in quantum mechanics, it allows a quantum system to then process, if you like, information in this large space of states efficiently. Okay, so these were the two insights of Feynman's, and maybe we'll go we'll skip past the next slide, please. So we can go past. And so this is one intuitive way to try and understand why it may be this case that a quantum computer is more efficient than a classical one. Let me see if I have, okay. And why there is so much excitement that perhaps we can build such fast quantum computers. Okay, the fact that you can do this kind of parallelism, and also, and this doesn't come out in Feynman's reasoning, but the fact that you can use entanglement. Entanglement is a key, because if you weren't using entanglement, then in principle you should be able to reproduce much of what is done with some classical system. Maybe you have to build a big one, but if entanglement is key to your algorithm, is key to how you're achieving the speed up, then because Bell showed that the effects of entanglement cannot be reproduced classically, you cannot do cannot hope to get the same kind of speed ups using classical hardware, using a classical system. Okay, so therefore you really need these various aspects of quantum mechanics. And this was well exemplified, and then I really will stop. I know I'm coming up to the limit. Peter Shor, in about 64, Bell wrote this landmark paper. The experiments get done, but it's really Peter Shor in about 93, I think, or 4, who realized that I can put quantum mechanics to use in computation. And what he showed, and this is another landmark result in the field, he showed that a particular problem, which is very hard to do in using classical computers, can be done really very efficiently, much more rapidly with a quantum computer. And the problem has to do with finding the factors, the prime factors of any number. Now, I'm very sorry, I had a slide here explaining what prime factors are, but it seems not to be there. So let me try to explain. If you take a number like 21, say, and I asked you, well, what are the factors? You'd say, oh, 7 into 3, right? So 7 is a prime, 3 is a prime, 7 into 3 is 21, right? Okay, well, I could give you another number, right? Maybe it has 3 prime factors. In some cases, maybe if I give you 49, it is 7 squared, so the same prime factor appears twice. So in this way, finding all the prime numbers which when you multiply together, maybe one prime number is multiplied more than once. But in this way, finding the factors of a number is called, the prime factors is called the prime factorization problem. Okay, and well, for 21, it's so easy to do. But as you take a bigger and bigger number, okay, as you take a number with n digits, this gets harder and harder if n is big. And I'll just give you the classical. If you try to implement the best classical algorithm today known for finding prime factors, it goes exponentially in log n to the 3. So now here I used n to be the size of the number. The number of digits is actually log of that, because, for example, if I use 2 digits, in decimal system, I can write a number up till 10. If I use 3 digits, up till 100, and so on and so forth. So the number of digits, little n, is log of capital N. But anyway, let's use capital N, the size of the number. So the classical time is log n to the 1/3 up to some small corrections, exponential of that. Whereas the quantum time used in a quantum computer, if we could build it, but the time that it would take if you implement Shor's ideas, Shor's algorithm for a quantum computer is just log n to some power. Okay, square, so you pay a price. But log n square is still a very much smaller number than exponential of log n to the 1/3 for any big number n. And so in this sense, it's an exponential speed up. And next slide, please. Next slide, please. Thank you. So now I'll skip over some of the details, what the algorithm involves and so on. But it's well worth reading about. Unfortunately, the best descriptions of Shor's algorithm are still a bit complicated. And I think they can be simplified. But at the moment, one does have to work through a slightly complicated set of notes or lectures, but it's not too hard. It's all rather simple algebra and so on. So it's quite explicit, and one can find this kind of result. Maybe someone will review it in the set of lectures you all have. Okay, next slide, please. Now, it's rather important, the fact that factorizing numbers into their prime constituents is so hard is actually very important in the real world. It turns out all the encryption, when we do credit card transactions online, you send your credit card number. We all hope it won't be stolen. The reason, or we do bank transactions, the basic reason for the safety of this, of the encryption which is used, is a kind of form of encryption called the RSA encryption. And it uses the fact that large numbers cannot be broken up into their prime constituents easily. So if you could build a quantum computer that does it exponentially more rapidly, then you are going to endanger all of internet commerce, a lot of banking and so on. So it's actually an issue of huge practical interest and importance as to whether one could actually build hardware to implement Shor's algorithm and factorize numbers into their prime constituents easily. Okay, so this is part of what is driving the progress in quantum technologies today. Okay, next slide, please. Just to tell you, in TIFR, we have Vijay Raghavan, who's built a 6-qubit quantum computer, which is India's first. And the next slide, please. There's interesting activity going on in India. Here's Vijay holding his qubits in front of his dilution fridge. Next slide, please. So there's activity. And just to say that, the National Quantum Mission has now okayed the building of a 20-qubit machine that will happen in TIFR, but actually it's a broader coalition. Collaboration. And the general idea of the National Quantum Mission is to really build capacity across all our various, constituent units, the research laboratories like TIFR, the universities, the central universities, the state level universities, and so on. And so it's really a very, very good time when you're holding this workshop, because, with a little bit of training, our students more widely can and should participate. And in fact, that is one of the key ideas behind this mission, which is now just getting going. Okay, now I'm just going to end my Atri, if it's okay, because we are already quite a lot over time. So I'm just going to end my talk, and I'll just show you a couple of pictures. And for that, I need you, Atri, to help me by going to the end of my talk.
Tell me the slide numbers.
Go to slide number 89, which has a picture of our Honorable Finance Minister. Thank you. So I wanted to, this is not a postscript, I'll come to the conclusions after that. But just to say, this is the Honorable Finance Minister, Nirmala Sitharaman, presenting now some years ago the budget where she announced the National Quantum Mission, and it took us some time, but it's actually getting going. And as I said, it has a hefty budget and a mandate to actually reach out all across our entire educational system. So stay tuned for opportunities this will offer, because one thing to say is that one aspect about working in this area experimentally is that it is not very cheap. Okay, this is a fact. And so you need some reasonable funding, and we must have that funding used to set up laboratories across universities so students can get a hand-on understanding. And as I said, there are so many things one can do. Working in this DRDO lab, we found it easy to build this random number generator, which is at the heart of encryption. And within a year, we had a system of communication as secure as the best in the world, which the armed forces are using today. So, and it didn't require very much of money, but it required some inventiveness. This was done in a DRDO lab. So there's lots of opportunities, even and especially in the experimental angles, which we should try to use in the country. Okay, if you don't mind going to slide number 86, please. 86, please, which is the conclusions, then I'll stop. So just to conclude, I hope this has been of some interest to you all. Quantum mechanics lies at the heart of our understanding of nature. Despite over a century of intensive study, we are only beginning to come to grips with how strange and weird it is, and understand that some of this strangeness, in particular entanglement, which is a kind of key property of quantum systems, as I tried to bring out, is also a resource for us to try and accomplish things which are otherwise near impossible in the classical domain. And building quantum computers is one example, but there are many others. There is also the fact I couldn't go into, which is that these ideas from quantum of what constitutes truly intrinsic quantum behavior, entanglement, and related ideas in quantum information are beginning to shape our understanding of more traditional branches of physics, whether it's condensed matter physics, whether it's the study of gravity, and so on. So it's both applications to technology and also, in a sense, I wouldn't call it applications, but connections with various areas of science, which makes it interesting. There's a lot of work in metrology, in sensing. I think you have some lectures on that, which I didn't go into, but which I'm sure you will cover, which also hold a lot of progress. So just to end, unexpected and exciting discoveries lie ahead in physics, but also chemistry, computer science, mathematics, as they intersect in all kinds of unanticipated ways, because they share many interesting ideas and connections through quantum mechanics. It's a very exciting time. India is poised for a real leap forward, as I brought out, I hope. And I invite you all to join in the fun and enthuse our students, who are ultimately our future, to take this great frontier, which is going to unfold now, forwards with great enthusiasm. Thank you very much for your time, and thank you for listening. Okay, Atri, that's it from me. Sorry for all the hiccups and so on.
Thank you.
Technology. Yeah. Yeah, Shanchali, please.
Thank you, Professor Trivedi.